video, I'm going to be explaining about the electronic configuration of transition ions and their respective atoms. Now, I didn't do this in the last video because, for example, chromium and copper, they do have queer electronic configurations. They have electronic configurations that are strange or that are different from the electronic configurations of S block elements, of the other elements or atoms that we discussed in the last video. Now, in this video, I'm only going to be focusing on the first row transition elements. I'm not going to include scandium and zinc because they are not classified as transition elements in our A-level course. Titanium is going to be the first element that we're going to look at. Titanium is 22 electrons. So those 22 electrons, we're going to look at the full electronic configuration. Then we're also going to look at the short-chain electronic configuration. 22 electrons are the full electronic configuration. We're going to have 1s2, right? Then it fills 2 electrons. We go to the next, we're going to have 2s2, the sub-level. This orbital gets filled with 2 electrons. Then the next orbital in this sub-level is going to be, the next sub-level in this energy level is going to be the P2, 2p, which will have 3 orbitals like that. We have 6 electrons, right? Then we have the next energy level, the 3, the energy level 3, which we have the sub-level 3s with 2 electrons. Is going to have the 3p with 6 electrons. Like that. 1, 2, 3, 4, 5, 6. Now, how many electrons do I have so far? I have 4. Then I have 10, 11, 12 plus 6. That gives me 18. And titanium, as we have said, is 22. So 18 electrons, 18 from 3p. We do not jump straight to 3d since 4s has a lower energy than 3d. So we come to 4s2. We're going to have 2 electrons there. Then we're going to have a 3d. It's going to have 5 orbitals. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5 orbitals. So 2 electrons are going to be residing like that. So the electronic configuration is going to be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d2. You will notice that the electronic configuration can be given as 1s2, 2s2, 2p6, 3s2, 3p6, 3d2, 4s2, with the 4s being the outer shell. How does the 4s become the outer shell? When I say that it has a lower energy level than the 3d. Now, when it's unfilled, right, the 4s and the 3d, the 4s has a lower energy level. But when electrons, right, let me put it in this way. This becomes the 4s. That's my 3d. Let me try to explain it this way. Now, when electrons come into the 3d, they repel this 4s. They repel it away from the nucleus such that it becomes the outer shell, right? and it's repelled away from the nucleus. Therefore, it becomes our outer shell. The concept is when the electrons come into the 3D, they repel the 4s, right? And the 4s becomes the outer shell. Now, these two sub levels, they have a small difference in energy. Therefore, they tend to act as one shell, especially in chemical reactions, which is why the 3D is able to repel these and not the shell, because the difference in energy is small. So it repels this outside, away from the nucleus. That's it. Now, the short-end electron configuration is going to be argon, which you said is 18 electrons. So 18 electrons, then here, which then we have 3d2 4s2 for titanium. This is the electronic configuration, the short-end electronic configuration. Now you can try that of vanadium and manganese. Let me jump straight to chromium and copper. Chromium, it has 24 electrons. So this is 22. Right, this is 22. This is 20. 3D. And 3D, I can have something like that. This is the expected electronic configuration for chromium, right? Because there's 24 electrons. From what I said, you first feel the 4s, then it gets repelled and becomes the outer shell. But this is not the electronic configuration. Rather, the electronic configuration is that 3d5 for S1. Why? Because a half-filled D sublevel is much more stable than that with the D4 electron. So it will rather have the one electron in the 4s get into the D orbital and make it half-filled like that. So this electronic configuration, this is that of chromium, is much more stable. Then for copper is 29. So the expected electronic configuration is going to be 4s2 3d9, like that. Right, but rather this is not the electronic configuration, as this is not stable as compared to the actual electronic configuration, which is 4s1 3d10. So we notice from these two electronic configuration, there's ones that are the fully filled and the half-filled electronic configurations. These are the most stable as compared to that 9 and the 4. Now this can be put with the 4s being the outer shell, like that. Those are the electronic configurations for chromium and copper. Now the electronic configurations of the corresponding ions. Let's look at titanium. Titanium, I said it's argon, 3d2 4s2. That. Now, titanium 2 plus, the electronic configuration, we're going to remove 2 electrons from the outer shell, which is going to be 3d2 4s0, or just 3d2, like that. That is the electronic configuration of titanium 2 plus, because the 4 the 4s is the outer shell. Let me take, for example, copper 2 plus. Copper 2 plus is, I've said, this is the electronic configuration of copper, 3d10 for s1. So this is it. We have 1 electron in the 4s. We have 10 electrons in the 3d. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 3d10. Now, if it loses electrons, it's going to lose this first one, this one there, and it's also going to lose this one there, such that I'm left with, for copper 2 plus, sorry, I'm left with 3d9 4s0. So the electronic configuration for copper 2 plus is going to be 3d9. If you want, you can put the 4s0, but it's not really relevant. That's how we put. So if it loses another electron, which is not stable, or that ion doesn't exist, copper 3 plus, this is not the electron that will be lost, but rather this one. Let's look at manganese. Manganese is as 25, right? 25. So 1 3d first 4s2 3d. So this is 20 25, like that. Okay. Then 4s2. Right. This is for manganese. Manganese 2 plus is going to lose both electrons from the 4s, right? Such that we're only left with argon 3d5, like that. But if it loses 2 more electrons, we lose this and that, right? Let me look at copper there, or the d orbitals. Yeah, if the electrons are paired like that, losing the electrons would first lose those ones, now the anti-clockwise spin, right? So if I would lose 3 electrons from that orbital, from that sublevel, sorry, I would have, suppose I lose 3 electrons, right? I'm going to have one like that. This is the electronic configuration that I have, rather than the tempting one, which this is what you'll be tempted to do, and please don't make that mistake. Right, like that, because you're saying you'd have lost 2 electrons and 1 electron. This is what you're tempted to, right? But don't do it. You'd rather you first lose the electrons with that spin, the ones which you would have ended with when ending, then you lose the other ones from the spin. So you lose 1 electron from each orbital first. Then when they are single as these ones, you can now lose from each orbital. So that is the end of the video. Stay in tune and wait for the next video on ionization energies.